Hello, welcome to the talk, Discrete Word Embedding for Logical Natural Language Understanding. And we're researchers from IBM. Much of today's AI research has been focused on two paradigms, the symbolic AI systems and neural systems. And today we want to focus a lot on the planning side, and specifically how can planning help with the task of language generation through building a discrete word embedding. And so that's where our research sits at. Classical planning is usually framed as with the initial state, a goal state, and a bunch of actions where the planners tries to sequence the actions together. And if you think of the task of language generation, it's really trying to combine words sequentially to achieve some sort of goal. So how do we formally think about this? So this is something that it will look like where we have a goal to achieve at the end of the sentence. Then we think of the action as each individual words, where we assume the precondition would be some sort of grammar, and the effect of the word would be the meaning of the word that it brings to the sentence. And with planner, you hopefully will achieve the sentence generation to achieve the task. But how do we learn this formal structure? To understand this, we'll first have to introduce word embedding, which is a distributed representation for words that NLP people nowadays use. And really what it means is that each word is mapped to a vector of continuous values. One of the most famous architecture is CBOW, continuous bag of word, introduced by Word2Vec paper. And the idea behind it is that a word is similar to the context around it. And this is the architecture. So to briefly go over how to train a CBOW, you really just need continuous sentences. You build a vocabulary based on the data. It's a hash table that maps the word to the ID. And the most important part of the CBOW architecture is just the embedding vector we're trying to learn, where the vector size is vocab size by the embedding size. And to obtain the word embedding, we basically just take the row of that particular index. To generate the data set, we use sliding windows of a fixed context length size, where the target word would be the middle word and the context side would be the flanking two lengths. Again, so this is the architecture for continuous bag of word. To understand it, it's basically summing the word embeddings on the left side of the context word, and we try to compare that to the word embedding of the target word. And again, the intuition of the whole model is that the meaning of a word is similar to the context. So we minimize the loss between the two sides to make the model learn over time. But however, how do we make this architecture plannable, right? To make something plannable, we first need to introduce the idea of sequence, and then we need to make the states discrete. So think of the model in a sequential manner. We sort of introduce this idea of a state, right? Instead of just having word embeddings, we think of adding the embeddings into a state sequentially, where each words contribute to the states, and then obtain the final effect of the context word. Similarly applied, we will do the same thing for target words and get the effect of the target word. And we compare the loss and back to the same thing. So really to convince you that the left side and the right side is basically the same architecture, because it's a continuous addition without really sequence, but we think of it as a sequential manner. But however, to make this architecture further more plannable, we need to make the states discrete. And how do we do that with addition process? And that's where we introduce the discretizer binary concrete operation. It's a fancy sigmoid function, which with a annealing schedule with annealing factor tau, with a little bit of logistic noise, and throughout the training, the temperature drops, and the function actually looks like a sigmoid to a step function over time. We utilize this training regime to apply a continuous word effect to a discrete state. We first have to use batch norm to continualize the discrete states at each step, and then we simply add the word effects with the continuous vector, and then we use binary concrete that we just introduced back there to discretize the states back again. To concretize this idea, we can then add some vectors into it. And once we learn model weights, we can then obtain the effects of each individual words by applying this word to a 0 vector and a 1 vector, and see which bits actually changed to obtain the add and delete effects. Just a note here is that through this mechanism, all the results is guaranteed to be strips compatible, because the word effects are independent from the state, meaning that there will be no conditional effects. And so apply what we just said, the BTL mechanism, Back-To-Logit, to our model. We're really just applying that sequentially over the context word to obtain the final context. And then we do the same thing with the target word to obtain the target effects. And we put a loss function between them to make the model learn over time. Once we have an architecture like that, we can sort of start performing semantic algebra in a discrete space. As opposed to a continuous vector, our model would provide 2 discrete vector, the add and delete effects. To add a word to a current state, we use progression through the set operation. And to subtract a word, similarly, we use regression. To really use this discrete operation in practice, we can refer to the task of analogy task used by original Words of Back paper to solve this idea that king is to queen as man is to woman. And in the embedding space, if the king subtract by man plus woman yield an embedding vector that's similar to queen, that means we have learned a pretty good semantic space. And to think of this in the discrete space, it's really simple, where you just separate the status and gender into 2 dimensions, and the words will follow in practice. And the analogy is really just trying to draw the 2 parallel arrows and then make sure that they are parallel to each other. And as you can see with our equations using our add effect terminologies, this example still holds. We actually evaluated our model on the analogy benchmark dataset released by Google, and we make sure that yes, we can see similar performance, if not better, in the discrete word embeddings as opposed to a regular CBOW. In addition, we evaluated our embedding on the task of word similarity and text classification, and found out that yes, discrete embeddings in fact do contain a lot of the semantic information that continuous embeddings does. And so in addition, we can use our discrete embedding for planning purpose. And this definition task is trying to plan for a sequence of words that will achieve the same goal as the word sushi, using the most frequent 4,000 words as actions. So we try to use regular planning where we need to reach the exact state. However, it's almost impossible because there are just way too many states to satisfy. So then we change to net benefit planning, where the goals are soft and constraints are easier met. So using Llama Planner, we actually obtained the sequence restaurant fish may be Japanese as the definition, as the planning result for sushi. We also have some other examples here that you can look at. And so in conclusion, we combined a word embedding approach to classical planning, where this discrete embedding actually captures similar semantic information as a continuous word embedding, and we also make sure that this word embedding is plannable through the definition task. Some future steps: we want to learn precondition for each action, we want to use hierarchical planning, and we want to think of the task more as a goal-oriented generation for dialogue and translation. And here are more examples. Thank you.